Hello everybody. I wanted to go over an example or two practical examples of how to use the second derivative test. In order, in this case, to find in number 4 here from 07, the time at which the particle is farthest to the left. That would be asking us, farthest to the left would mean absolute minimum value. I'm not going to do part B for number 4. That'll be for a different time. And then I'd also like to do part B in the 1998 number 2 question. Find the absolute minimum value of f and justify our answer and why that's an absolute min. So, yeah, let's get to it. Now, some of the parts of this I'm going to kind of gloss over just for the sake of time. But what I want to do in part A for number 4 is, first of all, I want to show or find a time at which x prime of t is equal to 0, and then determine if x double prime of t is greater or less than 0. So I want to find where x prime of t equals 0, and then at that value, or those values, t1 and t2, etc., I want to find out what the second derivative, or x double prime of t, would equal at those values. So the portion of this that I'm going to kind of gloss over is finding the first and second derivatives. Actually, I'll find the first derivative just because that will require a little bit of work here, but I'm going to gloss over the second derivative, and you can kind of work your way from x prime to x double prime. So x prime of t, right? We're going to take the derivative of position to find velocity. All right, so I'm going to use the product rule, which would give me negative e to the negative t sine of t plus e to the negative t cosine of t. All right, so I want to know where x prime of t equals 0. So I'm going to set this equal to 0. Factoring out an e to the negative t, I get cosine of t minus sine of t. Now this is in factored form, so I can use the zero product property on these two items to determine where x prime of t would equal 0. Well, e to the negative t is never equal to 0, so this will yield us no solutions. That was supposed to be a circle with a line through it. No solutions. Okay, but cosine of t minus sine of t is equal to 0 when cosine of t is equal to sine of t. And that's true within our bounds of 0 to 2 pi at two places. At pi over 4 in quadrant 1 and at 5 pi over 4 in quadrant 3. Okay, so I can say confidently that x prime at pi over 4 is equal to 0, and so is x prime at 5 pi over 4. So these are candidates for which we have an absolute minimum. Okay, now in finding the second derivative, now I've just, kind of determined now that I don't want to be lazy. I'm just going to do the second derivative here. So I'm going to perform the product rule on this expression, right, using e to the negative t as one function and cosine of t minus sine t as another function. So the derivative of e to the negative t is negative e to the negative t. And I'm going to leave cosine of t minus sine of t alone. Plus, I'm going to leave negative e to the negative t alone and take the derivative of cosine of t minus sine of t, which will be negative sine of t minus cosine of t. Now with the second derivative, my goal here is not to set this equal to 0. It's just to simplify it as far as I can, because then I'm going to test these two values to see what the second derivative evaluates to at those. Okay, so I'm going to pull out an e to the negative t Okay, so that's going to distribute then, this negative will be distributed to this entire term, which will make it sine of t minus cosine of t plus negative sine of t minus cosine of t. All right, so I can actually simplify inside a little bit further. Okay, you can see clearly that sine of t reduces with negative sine of t, and negative cosine of t minus cosine of t will give me negative 2 cosine of t. I'm going to simplify that just one more time, clean it up. I'm going to write this as negative 2 over e to the t times cosine of t. Now I'm going to evaluate, right, at both of these values, pi over 4. If I evaluate the second derivative at pi over 4, I'm going to get negative 2 over e to the pi over 4 times cosine of pi over 4. Now, this term here is less than 0, and this term here is greater than 0. Therefore, I don't even care what the value comes out to be, what its actual output is. I know it will be less than 0. Okay, therefore, what I know is that if x prime at pi over 4 is equal to 0, and the second derivative of the position function at pi over 4 is less than 0, that would represent then x of t has a relative maximum at x equals pi over 4. Okay. Let's do the same thing for x double prime of 5 pi over 4. Okay, I would get negative 2 over e to the 5 pi over 4 times the cosine of 5 pi over 4. Cosine of 5 pi over 4 is less than 0 because that's in quadrant 3 and the x value is negative there. So then I would know that x double prime of 5 pi over 4 would be greater than 0, which means that if x prime at 5 pi over 4 is equal to 0, and x double prime of 5 pi over 4 is greater than 0, then x of t has a relative minimum at x equals pi over 4. Now, how do I know whether or not that's an absolute minimum? Okay, so I would have to check my endpoints. I would check my endpoints and clearly see that if I plugged in a 2 pi into x of t, I would get 1 over e to the 2 pi times sine of 2 pi. Well, sine of 2 pi is 0. So x of 2 pi would end up equaling 0. X of 0 would also equal 0. Okay, so I would need to know, right, since I know that I have a relative minimum here, I would need to know what x of 5 pi over 4 is. So I'm going to plug that in and see if it's less than 0. X of 5 pi over 4 would be 1 over e to the 5 pi over 4 times the sine of 5 pi over 4. Now, I don't know exactly what this would come out to be, but I do know that it comes out to be less than 0. Therefore, it would be to the left of both of these positions. And since it's already a relative minimum, and I've checked the endpoints as well, I can say that the particle is furthest to the left at time t equals 5 pi over 4. Okay, let's look at 98, number 2, calculator allowed. Okay, so we let f be this function, f of x equals 2x e to the 2x. Since we're allowed to use a calculator, I would immediately, absolutely 100% right away, type in for y1, 2x e to the 2x. All right, now without doing the actual product rule and chain rule in order to come up with the derivative, in for y2, I'm going to use Math 8. Inputting the following with respect to x of y1 at x equals x. What that will do is when we graph this, that'll graph our derivative. All right, so that'll be f prime of x. Okay, now for the second derivative, I'm going to use the second derivative as well. I'm going to do the same thing, except I'm going to take the derivative of y2 at the value is x equals x. And of course, you have to input the following within the notation. And that right there will give us y, y prime, and y double prime when we graph them. All right, let's take a look at the graph. Okay, here I've got the graph plotted of y, y prime, and y double prime. I want to do a quick analysis on this. Okay, so if we're looking for the absolute min value of f, we want to know this minimum value, absolute minimum value here on y, or y1. Okay, now the first thing I have to do is if I have this kind of notation going on, I have to determine and show the connection between y and f of x. If I'm going to label this as y, I need to connect those two. Okay, next, I know that there's an absolute min right here. Okay, I don't know what the x value is. You can't simply say there's an absolute min there because it looks like it. What you need to do is you need to show that there's an absolute min there. And I know that this x value right here, at which this is true, is x equals negative 0.5. Okay, so I know that f has an absolute min at x equals negative 0.5, since now comes the analysis. F prime at negative 0.5 is 0, as you can see here. And f double prime at negative 0.5 is greater than 0, as you can see right there. So using the second derivative test, I know that there's an absolute minimum value there on f at x equals negative 0.5. Now, you might be questioning, well, why don't I test endpoints? This function is defined for all values. There is no closed interval, right? This is our only critical value. Our only critical value for y is at x equals negative 0.5. And clearly we can see that the first derivative is equal to 0, and the second derivative is greater than 0 for that x value. All right, guys, that's a little second derivative test for you. Hope it makes sense. Let me know if you got any questions.